Here's the quiz on ionic bonding and formula writing. And we've kind of said this might be one of the most important concepts of all first semester. It doesn't go away. Eventually, when we get into chemical reactions, we need to understand how these formulas are structured. And so in questions 1 and 2, we have some Bohr models. And the whole point of bonding is to get full outer shells. A stable outer shell, usually 8 electrons, is the goal of any kind of bonding. So if I have 1 valence electron in sodium, looks like there's 1 little electron in that outer level. 1 valence electron. Chlorine's got 2, 4, 6, 7 valence electrons. 7 electrons in the outermost energy level. Well, then we could just take this 1 electron from sodium and transfer it over to chlorine. 1 electron will be transferred from sodium to chlorine. Now, sodium's outermost level would be the 2nd, but it would be full with 8, and chlorine can gain 1 to fill the 3rd energy level with 8 electrons. Now, when you transfer electrons, you create charged ions. We never change the structure of the nucleus. We're just changing the number of electrons. And so the sodium nucleus will still have 11 protons. But if sodium loses that outer electron, because we're going to give it over to the chlorine, instead of 11 electrons, now I would only have 10 electrons. And so the balance of charge would give me an overall charge of +1. So when you lose electrons, your final charge will be positive because you're not changing the number of protons. You've got less electrons now than protons. Chlorine atoms will always have 17 electrons. Oopsies, 17 protons. Hello, protons. A neutral atom of chlorine would have 17 electrons, but now we're going to gain 1 for a total of 18 electrons. So anytime you gain electrons, you have more electrons than protons, and your charge is negative. Now, these final ions have electron structures that look like a noble gas. And 10 electrons is normally neon. 18 electrons, that's normally argon. So all these atoms are trying to obtain a noble gas electron structure. But the core is still sodium and chlorine. We're not changing the identity of the element because it's the number of protons that identify the element. We're just achieving an electron structure that looks like a noble gas because they normally have full outer shells. Number 3, we have another set of Bohr models, magnesium and fluorine. Which of the following statements describes the bonding that would occur between magnesium and fluorine? So as I look at these models, looks like there's 2 valence electrons in the magnesium atom, 2 in the outer shell, 2, 4, 6, 7 valence electrons in fluorine. Okay, so fluorine is in the business of gaining electrons. It's already got 7. And so we just need 1 more to fill the energy level. So maybe we could take like this 1 and transfer it, whoa, over to fluorine. But now fluorine's done. Fluorine would be full. We can only take 8 valence electrons. So the fluorine could take 1, but then what do we do with this guy? The magnesium has 2 valence electrons. So the best option is for magnesium to transfer 1 electron to fluorine, but then we would need a second fluorine atom to take the 2nd electron from magnesium. So in the end, I would have 2 fluorine atoms. So maybe on the other side, there would be like another fluorine, and it would have 1 valence electron, or say the first energy level would have 2 valence electrons, and the second would have 7. 1, 2, 3, 4, 5, 6, 7. And then magnesium could say, oh cool, I'll give my other valence electron to a second fluorine atom. Fluorine will each gain an electron. Magnesium will lose 2. But fluorine can't transfer 6 valence electrons because it has 7. So then there'd still be 1 random electron hanging out. Magnesium cannot give both electrons to fluorine. Fluorine can only take 1. And fluorine is not, again, in the business of transferring electrons to magnesium. Fluorine, which already has 7 valence electrons, would like to gain 1. It's really close to a full outer shell. Now, in general, it's the metals that will lose electrons. The metals already have like 1, 2, 3 valence electrons, so it's easier for them to lose a few to obtain a full outer shell. The nonmetals generally gain electrons. Nonmetals usually already have 5, 6, 7 valence electrons, and so they're in the business of gaining a few. So the metals are usually positive, the nonmetals are negative, which you can kind of see in a full picture on a periodic table. So in question 5, we were matching the groups with their charge, and so if you haven't already, I would highly suggest marking up the periodic table on the back page of your textbook. Everybody in group 1 is charged plus 1. They all have, let's say on the bottom I did like valence electrons. Everybody in group 1 has 1 valence electron, and so it's easier just to lose 1. That would be the alkali metals. The group 2 alkaline earth metals have 2 valence electrons, so it's easier to lose 2. And we form a +2 ion. Now the Roman numerals are used for the transition metals, tin and lead. Transition metals, tin and lead, can have multiple charges. Now put that in here too, multiple charges. And it's due to those big fat d orbitals that cause some irregularities, and that sometimes there can be more than one way of making an ion stable. And so you'll see a Roman numeral indicating the charge with transition metals, tin and lead. And then finally, when I get over to the boron family, they always have 3 valence electrons, so it's still easier to lose 3 than gain 5 plus 3. And for the most part, that's your metals. I mean, yeah, there's a few metals like tin and lead and bismuth and thallium, but there's your metals. They're all positive. Even the Roman numerals will always represent a positive charge. So if I see like iron, Roman numeral 3, it means iron plus 3. Which I should mention, plus 3, 3 plus, same thing. It doesn't matter if you go plus 3 or 3 plus. But now the carbon family is kind of funky in that carbon, silicon, germanium, they've got 4 valence electrons that they could lose 4 or gain 4. And so with 4 valence electrons, sometimes the charge is plus 4, sometimes it's minus 4. And eventually I'll show you how to figure that out. But then when we hit 5 valence electrons like the nitrogen family, now it's easier to gain 3. The oxygen family already has 6 valence electrons, so it's easier to gain 2. And when I'm talking about gaining electrons, I'm going to form a negative ion. The halogens already have 7 valence electrons, so they'll just gain 1. And the noble gases, for the most part, have 8 valence electrons, except for little baby helium, he only has 2. But the first energy level can only hold 2 electrons. So they really don't need to transfer electrons, and they have no charge. So if you can mark up your periodic table, you've got the charge on almost every ion, which is fantastic. And that's really going to help when it gets to the point where I want to write formulas. I want to start joining ions. All right, so then when I get to naming the ions, a couple little rules. I mean, obviously the metal ions are just their metal name, and the word ion If it's a transition metal, you'd see a Roman numeral to indicate the charge. The negative ions can have different endings. So if you just see the singular element, like nitrogen, just N, then the ending is going to turn to IDE. So IDE is just regular nitrogen. The ATE and ITE endings are called polyatomic ions. Polyatomic ions are on page 98 of your textbook. There's a chart. You don't have to memorize them, look them up. And I'll have that chart on the test for you. Okay, so the ATE ending is NO3 minus 1. And ITE is NO2 minus 1. You just look them up. But beware that the ending is the giveaway. If I see ATE, whoopsies. Yeah, IDE. If I see the ATE ending or the ITE, then I go to the chart. IDE is just the singular element. So something like number 7, SO4, when I see a group of atoms together, and often they're non-metals, they look like it could be a little formula, like SO4, cute. But it's not neutral, it has a charge. That's a good giveaway too, to go look at that chart on page 98. So the ATE ending is sulfate. ITE is also on the chart. It's SO3 minus 2. And then IDE would just be the singular element, just like it's found on the periodic table. Just sulfur minus 2. Now, the polyatomic charges, you also don't have to memorize. Somebody asked about it the other day, and they said, well, but if I add the normal charge of nitrogen and 3 oxygen, let's say, I don't get minus 1. You are correct. The charge comes from the fact that if you want to bond nitrogen with 3 oxygen and give everybody an octet, you're going to be 1 electron short. And so nitrate, for example, NO3 has a charge of minus 1, because I'm going to need to gain 1 electron in order to properly bond nitrogen and 3 oxygen and give everybody an octet. So you don't have to try to figure out the charges by like adding up the elements or anything like that. You just look them up. Page 98. But watch the way they're ending. So something like MgCl2, we've got magnesium, and the IDE ending represents chloride. So it's just regular chlorine, nothing fancy. So the chlorine turns to chloride. Chlorate with the ATE ending is a polyatomic, ClO3 minus 1. Often the 8s and 8s have oxygen in there. So just be careful of the way that it's ending. Regular chlorine, IDE. Now with magnesium, I do not need a Roman numeral. Magnesium is always in the group. That's plus 2. Plus 2 for life. It has no other option for charge. So you do not need a Roman numeral. But now copper we do. So the metal is copper. The non-metal is just oxygen. So it turns from oxygen to oxide. But before you call it done, just double check where that metal is coming from on your periodic table. So copper is coming from this middle transition metal group, and I do need a Roman numeral to indicate the charge. So to figure out what Roman numeral to use, we have to balance the charge. So you look up the charge on the negative ion, because the negatives don't have multiple charges. So if you find oxygen's charge is always minus 2, well, the point of these formulas is that if I totally transfer the electrons, the overall charge should be 0. These formulas should be neutral. And so if I know the negative charge is minus 2, there's only 1 atom of copper. I just have to figure out the charge on copper to make this add up to 0. That's some pretty complex math, right? How about a plus 2? Plus 2 minus 2 adds up to 0. So that charge plus 2 is your Roman numeral. Now, the wrong answer, I mean, all the other ones are wrong, but sometimes a wrong interpretation of this is that people will say copper 1 oxide because there's 1 atom of copper. And somehow they think that the Roman numeral is like the little subscript, the little number in the formula. Nope, it's the charge. So if you had like copper 1 oxide, you're saying that copper's charge is plus 1 and oxygen is minus 2. And then you get a totally different formula. If you were a charge balancer or a crisscrosser, you would find that there would be 2 copper, right? Like if I'm balancing this to get to 0, I'm going to have to multiply by 2. Or if you're a crisscrosser, you would be crisscrossing the 2 and the 1. And obviously then you don't bring down the plus or minus. It's a totally different formula depending on the charge of the copper. Number 10. Now here's another giveaway. Obviously Na is sodium. If you see there are 2 nonmetals on the back end of the formula, I guarantee it's a polyatomic ion. Look it up. There's no such thing as like sodium carbon-oxide. These ionic formulas only have 2 parts. There's the positive ion and there's the negative ion. It's just that some negative ions have more than 1 element. But the names are only going to have 2 parts. And so now if you see, oh, okay, I know this is sodium. And then what's this bad boy? Just look it up. CO3 is carbonate. Awesome. Another giveaway that you've got a polyatomic is if you see something like 11 where there's parentheses. Parentheses represents a group of atoms that all have 1 charge. Okay, so Fe is iron, and I know I'm going to look up NO3 on my chart, page 98, and I'll find that it's nitrate. And then again, before I say I'm all done, even with like 10 or 11, I should just look at my periodic table and see where these metals are coming from. Sodium is always in the group that's plus 1. Plus 1 for life. But iron is in this middle transition group. So sodium, no need for a Roman numeral. Sodium carbonate, done. But iron needs the Roman numeral. You can tell me, like, hey, write the formula of sodium carbonate. And I know I can look on the periodic table and find the charge of sodium. But if you just say, hey, go get some iron nitrate, write the formula of iron nitrate. I can't look at iron on the periodic table and find its charge. So I'm going to need the Roman numeral. Then we just work backwards. So you find the charge on the negative ion. Nitrate is minus 1. In this formula, there are 3 groups of nitrate. Another way of writing this would be like Fe, NO3, NO3, NO3. But that just gets to be a little bit annoying. So we shorten it up by saying, oh, 3 groups of nitrate, let's just put it in parentheses. And the little 3 on the outside tells me there are 3 groups. Okay, so negative 1 times 3 gives me an overall charge of minus 3 on the back. There's only 1 atom of iron, so it must be plus 3. And then again, it's that charge that becomes the Roman numeral. Iron 3 nitrate. Sweet. And even if I had this written out all crazy, it still adds up to 0, plus 3 on the iron, minus 1, minus 1, minus 1. It all adds up to 0. All right, now on the test, on the final unit summative, warning, you will see a lot of things like 12 and 13 where there might be like element X, element Z, or whatever it is. Element X is a metal. What is the charge of metal X in the compound shown below? So kind of like 11, if I want to work this thing backwards, the negative charge on oxygen is always -2. Then I figure out how much total negative charge. Well, oxygen's -2. There are 3 atoms of oxygen. So on the back side, this is going to give me a total charge of -6. Well, I got to make this add up to 0. So I need a +6 coming from my X ions. Well, there's already 2 atoms of X, and I want the total charge to be +6. So what if each X was a +3? Because then 3 times 2, the front side would give me a +6. So I want the total charge to be +6, but since I have 2 atoms of X, each X must be a +3. Kind of similar with number 13. X is a metal. What's its charge? Well, phosphate, this group in parentheses, is a polyatomic ion, and I can look up its charge on page 98. The whole group, PO4, is -3. If you bond phosphorus and 4 oxygen, and you want to give everybody a full outer shell, you're going to be 3 electrons short. Somehow you'll need to gain 3 more electrons. Okay, well in this formula there's actually 2 groups of phosphate. So that gives me a total charge, kind of similar, -6 again. But this time there's only 1 X ion, and so X itself has to carry the whole charge +6, so that they end up being neutral. Fantastic. Again, there are no negative ions that have multiple charges. So if you can figure out the negative charge, then I can backtrack and figure out how much positive charge I need to make the compound neutral. All right, and then we end it by switching gears and writing formulas. We are freaks about charge when we write ionic formulas. We're freaks about finding the charge and making this thing neutral. Now there's 2 methods to writing ionic formulas, but both require you to find the charges. You've got to find the charge. So you could use your periodic table to find the charge of potassium and oxygen. Then the 2 options are to either be a charge balancer, to say, okay, I need to make this add up to 0. And so if I take 2 potassium, that would give me a +2, and that would balance with my -2. +2 minus 2 adds up to 0. If I needed to multiply the charge by 2, then I need 2 atoms of potassium in my formula. Done. K2O. Now the other option is to be a crisscrosser, where you would just find the charges and crisscross the numerical value. So you could crisscross the 1 and the 2, and you get the same formula. And you don't have to write a 1 in a formula, and you don't bring down the plus or minus. Same thing with polyatomics. The whole group hydroxide has a charge of -1. Well, if I want to make this neutral with calcium being a +2, I could either take 2 atoms of hydroxide, and because it's a group, I want 2 of this group, I have to put it in parentheses. Which is why this first one is wrong. Like, this guy gets a sad face. Whoa, sad face. Because it looks like you only have 2 atoms of hydrogen and 1 atom of oxygen. But really, we're going to have 2 groups of hydroxide. If I want to write this out like the long way, it would be like calcium, OH, OH. There's going to end up being 2 oxygen and 2 hydrogen. So this is my +2, -1, -1. Yep, it's neutral. It adds up to 0. But you could also be a crisscrosser, and you would crisscross down the 1 and then the 2. But you just have to put a polyatomic in parentheses if you need more than 1 of that group. Now, The only time that you have to be a little bit careful if you're a crisscrosser is something like 16. So to refresh your memory on Roman numerals, V is the 5, 1V is the 4, V1 is the 6. So if the one's in front, you subtract it. If the one's in back, you add it to 5. So this is lead 4 sulfide. Sulfide is just regular sulfur. I can find its charge on the periodic table. It's in the group with oxygen that's always -2. And the lead now is +4. Transition metals aren't a big deal when you're writing formulas because the Roman numeral is just telling you the charge. But if you are a crisscrosser, you just have to be a little bit careful because we always report ionic formulas as the simplest repeating pattern in the crystal. So if I crisscross and I see 2 and 4, I really need to simplify that down to a ratio of 1 to 2. Now if you're a charge balancer, you're going to get that right away. Where if I'm balancing the charge, I see a +4 and a -2, and then I'll say, oh yeah, I just need 2 of these guys, and then it's neutral. +4, -4. Great, done. I need 2 atoms of sulfur. So the only time where the crisscross thing just takes an extra second to say, wait a second, I can't leave a 2 to 4 ratio in an ionic crystal. It's the simplest repeating pattern of the crystal. Ammonium is a goofy polyatomic. It's the only positive. People always want to say like Am. Am is on your periodic table, but it's americium. Ammonium is NH4. Its charge is +1. It's a big group. Chloride is regular chlorine, -1. So it's neutral. Polyatomic ions don't need parentheses if you only have one group, but it would be optional. Like if you did this, I'll put like a little dose parentheses in. If you left it as a 1-to-1 ratio and you did put parentheses around NH4, I would never mark that wrong. But like the third choice is wrong because I only need one group. I don't need 2 groups of NH4. So when in doubt, you can put the parentheses in. You only have to have them if there's more than one of a polyatomic group. And here we are, the last 3. Cobalt-3 sulfate. So the ATE ending means I need to look it up on page 98. I need to look it up on my polyatomic chart. Sulfate is -2. And that Roman numeral means cobalt is +3. So you could be a crisscrosser. And if you crisscross, I'm going to need 2 cobalt and 3 groups of sulfate. So I have to use the parentheses. You can't say like some people will go CO2SO4 3. Because now that kind of looks like SO43. It looks like we got 43 oxygen, which in reality we don't. That'd be crazy, right? Now we need to put this guy in parentheses to show that there's 3 groups. If you're a charge balancer, then you kind of look at this and say, well, I've got a 3 and a 2. So a common multiple might be 6. So I'll multiply this by 3, this by 2. Now I get +6 -6. And those multipliers then tell you how many ions you need in the formula. I'm going to need, no matter how I do it, 2 cobalt and 3 groups of sulfate. And then finally 19 and 20, these are, again, what you'll probably see on the test. Element X has 5 valence electrons. So if I think about 5 valence electrons, that puts it in the nitrogen family. Well, if there's already 5, I'm likely to gain 3 to get a full shell of 8, to get my octet. If I gain 3, That means X has a charge of -3. Potassium is +1. And so either way I do this, if I'm a crisscrosser, I'm going to crisscross the 1 and the 3, and I'll have K3X. Or if I'm a balancer, I'm going to say, oh yeah, I'll just take 3 of the +1 +1 potassium ions, and that +3 would balance the -3. Now, because X is going to be a -3, it's going to go in the back. So we always write our formulas positive, negative. So that's why the first choice, even though it shows the same ratio, but it's kind of flip-flopped. The 3 potassium should go first. The positive ion always comes first, followed by the negative. And the number 20. X is an alkaline earth metal. That's a group 2 metal, and they're always +2. So with it being a positive metal, X is now going to go first in the formula. When X bonds with chlorate, I need to look it up on my chart. Chlorate is a polyatomic ClO3 -1. That whole thing is -1. So if I'm a balancer, I'm going to say, give me 2 of those. +2 -2, that'll be neutral. And then because I need 2 of this whole group, I'm going to put them in parentheses. You could also be a crisscrosser, and then I'd be crisscrossing, get out of there. I'd be crisscrossing the 1 and the 2. And no matter what, I would get the exact same formula.